at somebody and see how much people are shaking or have like the dark lips of this cold place here, and we figure out what is the ambient temperature. Oh, jokes apart, let me. It's a great pleasure to introduce you to Professor Fabio Bozzoli from the Universita di Parma. Fabio works on heat transfer and very applied work on heat transfer enhancement, and also inverse problems related to how deposition, fouling, and affects heat transfer in pipes and heat exchanges, all that. And so, great pleasure to have you here, Fabio. Please.
Thank you very much. It's a pleasure to be here. When you invited me, you told me it was summer here, so very hot. Now it's very cold inside. It was a trick. So, thank you very much. Yeah, it's my presentation, but it's the result of a working group. I'd like to thank PhD, post-PhD students and associate and full professor that with me I'm working on this subject. It's a very practical case. I'm trying to focus on an application. Of course, our research is wider. So if you want to improve your knowledge about our research, Google me, find other papers, or ask me. So I come from Parma University, some details because it's a small city. Yeah, this is Italy, more or less. Parma is in the north of Italy. It's not far from Milano, so it's north. It's a small city. It's about 200,000 people, so a small city for Italian size. But the University of Parma is one of the oldest ones. The foundation of the university is maybe the 11th century. So it's a long historical university about every kind of research and field, from literature, arts, and engineering as well. So, some details about Parma. Maybe some of you already knows that, but Parma is famous in the world for music. If you are a fan of opera music, for example, Giuseppe Verdi was born in Parma, so lived in Parma. So if you listen to opera, maybe it was written and played in Parma. After that, movies. If you are a moviegoer like me, you should know Bernardo Bertolucci. He's an Oscar winner, film director. He directed Last Emperor, for example, but many other movies. He's still alive, he's still working. And after, from architectural point of view, the city of Parma is quite interesting. You can see a picture here of the city center. It's Middle Age, Renaissance time, so it's very nice. And last but not the least, the food. You can see, yeah, just a picture of tortelli di Parma. They are quite good if you want to try that. But, yeah, Parma, yeah, it's famous for prosciutto, this one, Parma ham, cheese, Parma cheese. When you say Parmigiano, means made in Parma. So every kind of Parmesan cheese is coming from Parma, if it's true. If it's not, if it's fake, maybe it's coming from China or something like that. But if it's true, if it's expensive, it's coming from Parma. But Parma has earned the reputation of being the Italian capital of taste, not only for the food, but for the companies. We have about 20 leading food companies, international leading food companies, that are settled down in Parma. Look into numbers, to money. The turnover of the companies in Parma is about connected to food industry. I'm talking about food, but also about plants, not only foods inside of dishes. The turnover is about $25 billion. That compared to turnover of Italy, that is 100 billion, it means that in a very small city, you have a lot of engineering aspect about foods. That's the reason why when I'm talking about heat transfer engineering, it's always related to food. So, first of all, saving nowadays in material, in energy, is extremely important. For this reason, when we have to design a commercial heat exchanger, you have to adopt such technique to improve, enhance heat transfer. You can't skip that. Also in food industry, it is very important. Saving money in terms of cost, space, and energy is important for every kind of application. Enhancement technique can be divided into active and passive techniques. In the active techniques, they require mechanical or electrostatic aids. This is an example. It's a scrap surface heat exchanger. You have heat exchanger, you have blades that are scraping the surface in order to remove the boundary layers. You need a field, you need energy to move that. Another case is electroacoustic, vibrating heat exchanger. You can vibrate, making movement somehow the exchange surface, improving in transfer like that. They are interesting, but they are quite expensive and complex. For that reason, passive techniques are much more interesting. In passive technique, you don't require any external power. In passive technique, you just change the shape of the surface, or you put inside some insert to change the flow field in order to enhance, increase heat transfer compared to the straight plane tube. Two classical cases are coils. If you just turn, you can improve heat transfer. Or if you are adopting corrugation on the surface, you can improve your heat transfer very much. Another kind of devices, passive devices, is inserts. Inserts are elements that you are placing inside the tube, and they help to enhance heat transfer. They are extremely interesting because they are quite cheap, and also the installation is very simple, and also the maintenance is very easy. You have just to remove, clean them, and put them inside again. So, among these kind of devices, one of the most important and biggest group is a category named displaced enhancement device. The name is a little bit tricky. Why it's called displaced? Because are devices that are not changing the surface, but they are changing the mixing inside. So they just displace, it means move, the fluids from the wall to the center in order to mix everything. So some cases, quite easy, are conical rings. You have some devices like that are moving the fluids next to the surface, or pipe-shaped insert. There are microchannels that you place inside, microtubes, or you have a lot of shapes. It's stripes inserts, so you have these stripes that are mixing the bulk. And if you have phase change, for example, could be interesting, putting inside some drainage insert that move the droplets from the surface to the center, and so on. In this paper, we are dealing with this kind of devices, and in the majority of the paper published, they are very common. They are really deeply investigated, but usually you find the performance only in terms of average heat transfer value. So you measure the input, the output, the average temperature, so you have a global performance. It's not easy, it's rather impossible to find some local measure about that, about heat transfer performance, because they are quite complex. It's not easy to place sensor inside. And as you know, measuring flux is not really so easy. And moreover, usually you have fluids that are acid or high temperature, so they destroy the sensor. So the aim of this work is filling this gap. Try to estimate the local behavior in terms of heat transfer of this kind of strange-shaped devices. Of course, a way for overcoming the limit of placing sensor inside is using inverse heat conduction problem. That's the main idea of our research. we are going to measure the temperature on the outer surface, and we are going to estimate what's happening inside. It's a classical, very easy from theoretical point of view, inverse heat conduction problem. Let's move to the experimental setup. We are going to study a butterfly-shaped device. It's called butterfly shape. You can see here it's printed with a 3D printer because the shapes reminds the shape of a butterfly. So you can see on that you have two wings. When I'm talking about wings, means this part of the inserts, and you have two indentions. So it's not exactly a butterfly, but it reminds it. So let's talk about the setup. The devices are fixed on a thin reed placed in the middle of the tube, and they are made by plastics, and they are placed inside a stainless tube of about 13 millimeter. So look into the device, it's 13 millimeter, and it's placed inside a tube of 13 millimeters. It means that the position is perfectly fixed. You have just a small contact between the insert and the surface in few points, but it's important to center that. Otherwise, it's moving, it's not easy to keep it fixed. In this case, we are focusing about turbulent flow regime. You can find this kind of devices applied to laminar, but also turbulent regime. We are focused on that. And for this reason, we are going to use water or glycerol, for example, for studying Reynolds numbers that are interesting in this case. This is a sketch of the setup. Let's spend some time. So this is the pipe. In this pipe here, more or less, you have the insert, the device inside. We are going to heat it up, and the easier way to heat it up and maintain it visible is using Joule effect. So you place two electrodes, and you connect that to a power supply. So you have electricity that are heating up the surface. Not only the surface, the volume of the tube, I mean. So we have a volumetric pump, yes, so the fluid is circulating in that way. It's important to have a holding tank. In that way, you can mix everything and keep very steady state. We are going to study steady state condition. You have to keep it steady. Later on, you will understand why it's important that it's very steady. So you need a very big holding tank. As far as it's a closed loop, you need a secondary heat exchanger to keep the temperature inside in the inlet section fixed. You need time, you need some hour to reach the steady state condition in a setup like that. But you can reach that. Moreover, it's quite important to have an air separator, because sometimes you have bubbles of air inside, and they are perturbating very much your experiment, creating something that is not steady at all. So it's important the separation between the liquid water and the fluid that is captured sometime here in the mixing or in your circuit. For keeping cold in the secondary exchanger your fluid, usually you are using cold water, but you can use what you want. Usually we are using city water because the temperature is very fixed, it's quite inexpensive, so it's an easy way to do that. Let's focus on this section, on this area. You can see here we have a thermographic system. Thanks to our infrared camera, we are going to acquire the temperature on the surface. That's the way we are going to acquire the temperature. So let's see here. This is the heated section. We have some insulating material to keep it quite insulating, of course, but you need a test section that is not covered. Otherwise, you can measure the temperature on the surface. It's not so difficult to do that. You uncover that, and thanks to this infrared camera, you can acquire the temperature. To do that, you have, of course, moving that around and acquiring different images to merge together. That's the reason why you have to be in a steady state. Because as far as it's a very sensitive camera, it's very expensive. So you can't have many of them. You have just one. So you have to move that, and for that reason, you have to be sure that you are in a steady state condition. So about the test section here, it's very important that emissivity is constant. You have a high emissivity surface, so you have to coat it with a very thin layer of painting with high emissivity. You know the emissivity, and it's very important to keep the environment and a fixed temperature in order to exactly measure the temperature of the surface, because it reflects a little bit. Yes, you can see here you have the electrodes, and the fluid is entering from this section, so it means that we are going to study the fully developed condition. We are putting the device in the fully developed region from fluid dynamics and thermal point of view. About the camera, it's a FLIR camera. It's a very high quality camera because the temperature difference is very small. This camera is a sensitivity of about 20 microkelvin, that is very small. It's not the error, it's the sensitivity. It means that it can catch difference of about this quantity, of course. And it's a high density sensor of rate density of about 640 sensor for 512. So a lot of points with a single image. So some details about the estimation procedure. First of all, we are heating up the section of the tube by the Joule effect. We are going to acquire the surface temperature, and solving the inverse heat conduction problem in the wall domain, we are going to estimate heat transfer rate inside the tube. We are going to estimate it point by point. So a spatial distribution in the inside surface. So in our inverse problem, the input is the temperature distribution on the external surface, and what we want to estimate is the heat transfer density on the internal surface of your tube. So quite classical heat transfer heat condition problem. Of course, if you have to solve an inverse problem, you have to model your reality in a certain way. In this case, we are modeling just the tube wall. We are not modeling convection inside, just the tube wall, because we are interested in what's happening on the surface, on the boundary condition. So it's a classical 3D model. It's a cylinder, very easy. So how we describe that? We have the energy balance in the solid domain. So it's just the wall, our model, nothing more, very easy. Of course, you are heating it up by Joule effect. So you have each source inside the volume, of course. After the key point are the boundary condition. Looking at the outer surface, we have external boundary, and it's classical. Rm is a thermal resistivity between the surface and the environment, where Tm is the temperature of the ambient, the environment. You can estimate this one quite easily. The sensitivity of your problem to this quantity is very small. If you double that, the results are almost the same, because you have natural convection with air outside, while inside we have forced convection with water. So the magnitude is completely different. So it's not a problem to overestimate or underestimate this quantity on your results. The key point is the internal boundary condition. So it means that we are going to estimate heat flux density in the surface, on the surface between the wall and the fluid inside. That is the quantity that we are going to estimate. I look to the coordinates. Alpha is the angular coordinates, And zeta is the axial coordinate. Of course, we have also radial coordinates, but as far as we are going to estimate on the internal surface, the radius is fixed in that point. Of course, two boundaries are missing in this case, are the side boundaries. It's not easy to understand what kind of boundary condition we are going to apply in the real life, but if you look at to the setup, if the test section is long enough, it's quite acceptable to think that the temperature here, the gradient, is close to 0. You can neglect that. Because in this section, you don't have strong variation. It's like having a straight tube, so axial variation is very small. So next to the sign boundary, adiabatic condition can be adopted. And we are going to check that on the experimental data if it's acceptable. Let's move on. Of course, we have a continuous domain, and we are moving to a discrete domain. And to do that, you have to simplify convective heat flux distribution, adopting, for example, a continuous piecewise linear function. It's linear, it's continuous, it's piecewise. So this is the expression of one of that point. So it means that you have to choose a grid, and in that way, heat flux distribution is defined by the value assumed at the nodes. So going from a continuous function to a discrete function make your problem expressible in a matrix form quite easily, where T is the vector, or the discrete vector of the temperature on the external cold surface. Q is the heat flux vector on the fluid internal wall surface. So it's quite simple, normal, metric expression of classical linear problem. Some details about X. X is the sensitivity matrix. Is describing the geometry in a certain way. To calculate that, you can do that quite easily from numerical point of view. For example, using two-point different approach. You solve your direct problem. After you perturbate that, just increase one of the value and calculate each element of the sensitivity matrix. As far as you are generating some heat inside the wall, you have also this constant vector that is not very common in this kind of problem, and it's quite easy to be determined. Just you have to solve one direct problem considering the heat flux on the internal surface equal to 0. Because you have internal generation, so you have an not homogeneous term. So you have to consider that. You could move that on the other side and the problem get homogeneous, just considering the difference, the relative temperature, for example, or something like that. So the techniques to solve that is the classical Tikhonov regularization method. You know that we are talking about that in almost each presentation. So you just move to a ill-posed problem, you overcome this kind of ill-posed nature, defining a cost function. You have, yes, it's an average, a weighted average between the residual and the smoothness of your solution. The key point is choosing regularization parameter, lambda, because it's not easy to choose that. And this drives your results very strongly. So we are going to adopt the classical Morozov principle, discrepancy principle. It means that you know something about the noise on the temperature. So you drive, you tailor that parameter as far as the residual, the average value of the residual is equal to expected noise. So let's go on. First of all, we are going to validate this procedure from numerical point of view. It's the classical way. We are adopting synthetic data. For doing that, we are adopting a geometry that is quite similar to the experimental Y, not very far. We are imposing a known distribution of Q. This is the function that we are imposing. It looks like, a spiral, something like that, because it's varying respect that radial coordinates, alpha, and axial coordinate. It's a plane plot of what's happening on the internal surface. So it's varying a lot. You solve the direct problem. You spoil your data temperature with random noise, and you use that for solving your inverse problem. You compare what we are imposing with what you found. Of course, it's a sort of inverse crime, but if you solve, for example, direct problem with COMSOL, and you calculate, for example, your sensitivity with MATLAB with a different approach, you can overcome it a little bit, not too much. A little bit you can overcome that. So let's move to results. Some numbers about this matrix. First of all, about temperature. We are considering 180 angular position and 550 axial position. It means 99,000 elements, a lot of elements. After about heat flux, exactly the same grid, something like that. It means 180 angular position and 550 axial position. So it means that the matrix of heat flux is composed by 19,000 elements, a lot of elements. If you look at the sensitivity matrix, it's crazy. It's a very huge matrix. It's something like 99,000 rows for 99,000 columns. It's a huge matrix from that point of view. Let's try to plot it. You can plot it, for example, for one source point. You can look at the sensitivity matrix. It's rearranged on the plane. It's a line in that case. But you can see that the problem is very sensitive, close to the source. And as far as you are going farther, the sensitivity is going down closer to 0. If you move the source close to the boundary, side boundary, you can see that the effect on the other side of the domain is practically not noticeable at all. It's interesting to give a look to the sensitivity matrix, how it looks like, because it gives you some information about the approach we are going to approach. Some details about the practical point of view. It's not easy to calculate that from numerical point of view. If you increase the number of points, it means you have to solve your numerical problem with very point sources. And you know, if you are very small and point sources, you need a huge mesh to solve that, to solve your problem. So let's compare. It's a case with very low noise. Let's compare exact, so the imposed and the estimated one. More or less, it's working pretty well. You can see some artifacts close to the boundary here. You can see, we can zoom later on that. Of course, we are going to plot, for example, the values for one angular position. And you can see that the match between the exact in blue and the restore in red is very good, except to the boundary, the side boundary. That condition is a little bit tricky, but it's quite common in inverse problem. Close to the boundary, you have less information. So it's not so easy to estimate correctly your quantities, because you are missing some information. You have more information in the center than in the boundaries. So we have one that tests for different noise level, and you can see the average estimation error versus the average noise level. And you can see that for low noise level, the error is something like 1%. So it's very good. From experimental point of view, we are expecting to be something like here. So between 2% of the estimation error. Let's go into the experimental setup. This is a picture of our experimental setup. Of course, we have to move the camera. This is the support of the camera. We are moving that in 6 position. it's important to keep it orthogonal to the x of the tube in order to minimize perspective problem. So if it's orthogonal, it's easier to reconstruct the temperature later on. Some picture about that from two different positions or something like that. You can see that the picture. Another key point, you need references, because when you have to mesh together images, you need references on your domain. So you have some label that you can see in the infrared that enable you to merge all the image. Of course, it's not only a problem of merging, you have to correct the curvature. It's quite easy because it's a cylinder and you're rather far from the cylinder. So you have to move from the projection coordinates to the cylindrical coordinates. The equation is extremely easy. You can calibrate that, for example, with a no pattern or something like that, if you don't know some of that geometrical parameters, but it's quite easy. So we have 6 images. We correct them for perspective, so we make them flatter. And after that, we cut and merge together. In that way, we have a continuous map of the temperature on the external surface. This is a night plot. You can see that the temperature is higher here, and after you have colder points or something like that. But it's very good from qualitative point of view. It's better to plot like this. So here you have z, that is the axial coordinates. This is alpha, is the radial coordinates. The position of the butterfly insert is here. So you can see something. First of all, you see that in the side boundaries, gradients are close to 0, as we expected, because the perturbation of the insert is just close to the insert, not before and not too far from that. So adopting a adiabatic condition on the boundary from experimental point of view looks acceptable. After that, you can see that you have noise, of course. You can see some random noise, but you have also some artifacts due to the merging procedure. Because yes, it's steady state, but it's not so steady. Differences are very small. You can see the map is going from 90 degrees to 21, so you have difference of 2 degrees that are very small from that point of view. So if you are merging something that is not so in steady state, use some linear artifacts here. So first of all, let's consider the average performance of this device. We are going to consider the average Nusselt number, the classical approach. Is defined on the average heat flux density. We have the average surface temperature and the average bulk temperature. You have to measure that, placing some sensors, some thermocouples inside the tubes in the inlet. And you can see here it's a comparison between the average Nusselt number of a pipe without the insert, classical correlation, and our case with the insert. And you can see that we have an heat transfer enhancement of about 80%. So it's working pretty well for the same Reynolds number, of course. Let's move to experimental results. It's not easy to estimate the noise level. That's the key parameter for the discrepancy principle. One way is just keeping the temperature on the surface constant, acquiring that, and finding the standard deviation of the temperature. It's a way for estimating that. But it's not exactly what's happening in reality, because we are merging different images that are not flat. So another way is adopting the classical L-curve plot, and you can see the knee is something like this, and so the noise level is something like 0.1 Celsius, and is exactly more or less the same that we have obtained estimating on the measured temperature in a constant condition on the surface. So We have two elements that confirm that the estimation of the noise level is correct. Let's move to results. Let's see one case, 8,800 Reynolds number. This is heat flux density. This is the position of the inserts. You can see here that you have some maximum and minimum close to that. To make the results a little bit more general, we can consider a parameter called local heat flux efficiency. Is the ratio between the heat flux with the insert and the heat flux in a plain tube without the inserts. So if it's higher than 1, it means that it's higher than the tube without the insert. If it's lower, it means it's below that. You can see that you have a minimum, and it's in correspondence of the wings. Of course, the wings are against the wall, so you don't have fluids that are flowing between the wings and the wall. So it means the heat flux close to the wing is very low, but before that you have a maximum, and it's due to the fact that we are mixing, we are deviating in a certain way fluid velocity. And after we have some interesting waves after the inserts where heat transfer is increased. And this behavior is similar, remind me something that you observe, for example, in the classical external flow on cross cylinder. You have waves after that are increasing heat transfer in that point. So it's a mixer, it's an enclosure, but some effects are almost the same. Let's plot that in an axial position. So it's the value around the angle, something like that. And you can see that you have the minima here, close to the wing. The maximum is not in the induction, on the side of the wings, where the fluid is forced to change its velocity, where the boundary layer is thinner and the mixing is higher. So it's very interesting from that point of view. So you have peaks that are something here, not in the middle, but close to the wings. Let's see the effect, for example, of the Reynolds number. If you are increasing the Reynolds number, so if you are increasing the velocity, and you plot exactly the same distribution, you can see that the maximum and the minimum are smoother. The behavior is much more smooth. So if you increase the velocity, the mixing effect enables you to mix in better everything. Let's see the same results fixing the angular coordinates versus the axial coordinate. And you can see that you have a maximum. The maximum is exactly in front of the insert, where the velocity has to be changed. We have a high gradient of velocity because it has to change the direction. And after, of course, you have a minimum where you have a stagnation point or a contact point between the insert and the surface of the tube wall. And after you have another minimum, it means that we have maybe, we are not sure about that, we have a stagnation point on the back side of your insert. So, same effect about Reynolds number. If you increase Reynolds number, you are smoothing. You are increasing the heat transfer, but you are mixing better. So, conclusion. We have adopted and tested an experimental procedure based on inverse heat conduction problem to estimate what's happening locally inside these kind of devices. These results are interesting, first of all, because you can design these kind of devices from local point of view. Because in some practical application, it's not only the average performance important, also the local. Talking about food industry, for example, if you have to pasteurize milk, it's important not only the average temperature, but also the local temperature. Because if you overheat your food, you destroy everything. You change the taste, And if you underheat it, you don't kill the bacteria. So it's important, as far as it's a very strict thermal process, to control not only the average temperature, but also the local temperature. And moreover, these data are quite original and can be employed for the validation, for example, of numerical models. We have wonderful numerical software, but they are usually validated on average heat transfer coefficient, never on local ones. And you can try to validate that on local experiment, and you can find some unexpected results, because they are working on the average, never on the local. It's very difficult to make them working. Next step, of course, we are going to study different geometries, either configuration. Thanks to 3D printer, you can change almost everything about that in order to optimize that. But the most important stuff related to inverse problem, we are going to use that like a benchmark for different estimation technique. So if you want to test your technique on our data, they are available. You can test your approach on 3D cases that are very experimental case, a lot of data set that you can employ. We are going to employ a reciprocity functional approach, for example, Gaussian filtering approach, but many other approaches are available for solving this kind of problem. And last details, if you look to sensitivity, maybe is it useful to use an all domain approach? Maybe it could be better to employ some local optimization approach, because sensitivity is going to 0 as far as you are moving from the source point. So it's just an insight in this problem. Thank you for your attention.
Thank you very much for questions.